We present closed-loop tool manipulation framework that simultaneously estimates and controls contact states using visual tactile measurements. Humans can perform very complex and dexterous manipulation tasks by reacting to sensor observations. Robots, on the other hand, cannot perform reactive manipulation, and they mostly operate in open loop while interacting with their environments. The design and implementation of closed-loop control for dexterous manipulation is very difficult because there are many unobservable contact states. Also, there are non-trivial mechanics, which makes the design of planning, control, and estimator quite challenging. With this motivation, in this work, we present design of planning, estimation, and controller for tool manipulation using tactile sensing. We present analysis of mechanics of tool manipulation, which provides a planner with physical constraints. Then we employ trajectory optimization to find the trajectory of the object, tool, and end effector simultaneously. Given the reference trajectory computed from the proposed trajectory optimization, we present our online estimation and control framework. Under unexpected contact, our tactile estimator estimates the pose of the object and tool using visual tactile sensors. Then using this estimate, our MPC-based controller is able to track the reference trajectory in closed-loop fashion. In this work, we consider the following assumptions to derive the mechanics of tool manipulation. However, in this work, we do not assume that the following parameters are known: length of the object, global position of the object, and angle of the object. Then now we are ready to present mechanics of tool manipulation. First, we have force and moment balance equations to satisfy the stability of object and tool. Next, we consider friction cone constraints to avoid slipping. Finally, we consider force controller constraints. The manipulator can only apply the forces along the axis where its motion is constrained. Next, we will talk about offline motion planning using optimization algorithm. We formulate the planner using nonlinear programming. This non-convex optimization problem can be efficiently solved using the off-the-shelf solver such as IP-opt. Next, we discuss the design of our online estimator and controller. For controller, we simply run trajectory optimization in receding horizon fashion. For estimator, the goal is to estimate these parameters. The key strategy here is that we can represent point PB as a function of this unknown variable using forward kinematics, as you can see here. Similarly, we can represent point PB using joint encoders, tactile sensor measurement, and non-tool kinematics. Then now we can do online nonlinear least square regression to estimate these unknown variables online. Then we show results of our framework. We use Mitsubishi robot arm as 6DOF robot arm, and we use Jetstream as visual tactile sensors. We use stiffness controller to implement our solution from trajectory optimization. In MPC, we keep updating those reference trajectories. We first show the results of open loop controller. Here the robot could successfully achieve pivoting. Next, we show the results of open loop controller for different object tool pairs on different contact surfaces, and as you can see, our framework could successfully achieve pivoting. We observe, however, following failure cases. At t equals 0, the tool slips against the object. Similarly, if the tool pushes the object too strongly, the tool rotates in the gripper and it loses the contact in object. Also, under unexpected contacts, the tool loses contact with object. To deal with these issues, we test our closed-loop controller. Here we compare the performance between open-loop and closed-loop controller with disturbances at t equals 0. As you can see, our closed-loop controller could successfully achieve pivoting, while open-loop controller failed. Finally, we added the disturbances randomly over the trajectory to test the robustness of our proposed framework. We could verify that our framework could successfully perform tracking of pivoting under several different unexpected disturbances.